Okay, this is chapter 4. It's going to be about integers and rationals. So let's start. One thing that's going to be defined here, or clear from our definitions, is that we're starting backwards, right? So for example, we know that a minus b is equal to c minus d if and only if a plus d equals b plus c, right? We know this. This is a fact that we know. However, what we're going to do is we're going to use this to define the definition of what subtraction means. It's going to be more clear, so I'll just start. Let's start with the integers. So the integers are defined as equivalence classes. A long bar b is equal to c long bar d if and only if a plus d is equal to b plus c. Okay, let's pause. What did we do here? We're saying an integer is an expression a bar b. Bar does not mean subtraction. Later, we'll see that, well, actually, bar does mean subtraction. But right now, we don't know what bar means. We're just going to say it's an equivalence class, right? And we're saying that a bar b is equal to c bar d if and only if this expression is true. And we can do this because a and b are natural numbers. And we know how to add natural numbers. So essentially, a bar b is the equivalence class that's isomorphic to have a natural number here and a natural number here. So we say that we can really write this as an ordered pair, right? A, B in n squared. So the first one's in n and the second one's in. All right. Now it's not hard to check that this is well defined. That is, like, if we have a bar b equal, well, actually, let's go on to laws of algebra before we check like well definitions and whatnot. So we define laws of algebra such that if we have a bar b, this is not subtraction, this is bar, plus c bar d, we'll define it as a plus c minus b plus d, or bar b plus d, not minus. And likewise for product, a bar b times c bar d is defined as ac plus bd bar ad plus bc. Now these definitions are well defined. That is, if we have a bar b is equal to a prime plus b prime, then we can substitute either one and get the same expression. Not hard to prove it, just using algebra and the natural numbers. So this is a definition, right? We're using our knowledge of what subtraction should look like, and we're getting a definition of the sum and product. Now we can finally say that, well, actually, we should embed. Let's embed the natural numbers in the integers. So we'll say that a natural number n is embedded as n bar 0, right? So n bar 0 means n, and n means n bar 0. This is an isomorphism. And now, just a few more things, and we can finally define subtraction. We'll define negation first. Negation. So we'll say that a bar b, the negation of a bar b is b bar a. So negation swaps the two. And now we can say that we let a plus negation b, where a, b, are integers, equal a minus b. And we notice that subtraction and bar. So we notice that subtraction and bar work the same way. Work the same. And now bar is useless. We can discard bar, right? Because we've basically just shown that we don't need bar anymore. Bar is just negative. One thing that I also want to get into is trichotomy. So in chapter 2, we did trichotomy of natural numbers. Likewise, we have trichotomy of integers, right? We have either x equals 0, x equals a natural number, or x equals the negation of a natural number, where n is positive and n is in n. So namely, n can't be 0, right? So how do you prove this? Well, it's not hard to prove. You just use the negation of integers and you do like a case by case basis, right? You can say like, oh, if first of all, you can prove that all three of at least one of them must be true. And then obviously you can't have two of them because that contradicts properties of the natural numbers. All right. So now with all of this, we can say the following proposition. We can say that um, integers form a commutative ring. What does this mean? This means that integers are commutative, associative, and have identities. Namely, the additive identity is x plus 0 is equal to x, and the multiplicative identity is x times 1 equals 1 times x is equal to x. And we also have inverses, right? So ring means we have an additive inverse. The additive inverse is the negation of x. A field means that we have a multiplicative inverse, but we won't get that until we get into Q, which is rational numbers. Okay, so now let's move on to a few more propositions of the integers. One of them is that integers have, if you have a b equals 0, then either a is 0 or b is 0. How do we prove this? Well, it's not hard to prove just saying like, oh, a equals like m and b equals, I'm running out of variables, jk. And it's not hard to prove by substituting it in and then noting that since zero is a natural number, n equals 0 means that n equals 0 bar 0. And you can show that this is only equal to 0 bar 0 when a equals 0 or b equals 0. A corollary of this is that if AC equals BC and C is not equal to 0, then we get A equals B. How is this a corollary? We factor this. We have commutative ring, right? So we can factor. We get C times A minus B equals 0. And from here, it's not hard to show that either C equals 0 or A minus B equals 0. So if C is not equal to 0, then we have A equals B. All right. So we have ordering. It's an ordered ring, right? Ordering. How do I do this? Yeah, so ordering. So we say that n is greater than or equal to m means that n equals m plus a, where a is a natural number. And we have the same things. Like if we add things to both sides, the equality changes. The equality stays the same. The inequality stays the same. One thing that we should note is that if a greater than b, then the negation of a is less than the negation of b. Right? How do we prove this? Well, we can add a to both sides and add b to both sides. Wait, no. Negation of b is less than negation of a. Sorry about that. Negation of a's. And then if we add b to both sides, we get 0 is less than b minus a. And add a, we get a is... Wait, what am I doing? Negation of b is greater than negation of a. There we go. And if it's positive, we can prove that the direction doesn't actually change, right? Okay. Now we can move on to let's see, what else is there? Yeah. I'm comfortable. Yeah, there's not really much more for the integers. So let's move on to rationals. One thing to know for the integers, though, is that induction fails, right? That's why induction is uniquely for the natural numbers. Let's move on to rationals. So rationals are defined as again, we can't use our notion of division yet. So we're just going to say, we're going to use equivalence classes AB, so basically rationals consist of ordered pairs in Z squared, where both of these are integers. So AB equals CD if and only if A times D equals B times C. and note. Well, I guess this should really be z times z cross 0, or z minus 0, right? Because we can't have 0 for denominator can't be 0. Or we haven't defined a denominator, but the second term can't be 0. We can easily prove that this actually forms an equivalence relation. That is, it's reflexive, symmetric, transitive, all that good stuff. Now we can have sum and product defined. We're using our knowledge from beforehand. We're saying that A cross cross B plus C cross cross D is equal to AD plus BC cross cross BD, set equal to. And we're saying product A cross cross B, this is a definition, times C cross cross D is equal to AC cross cross BD, set equal to, definition. And finally, we have the negation of A cross cross B is defined as negation of A cross cross B. Now, we can prove that this is well defined by noting that if A cross cross B is equal to A prime cross cross B, then we can substitute the expressions, and it all works very nicely. All right, so these are actually enough to prove a lot of good algebra for the rational numbers. Namely, we can embed. We can embed an integer z as A cross cross 1. This is an if and only if, right? So we say that A cross cross 1 is A, and A cross cross embeds to A, and A embeds to A cross cross 1. And it's not hard to prove that this works in both directions, right? Because you use the, well, you can say, like, what can we say? So we can say that if A cross cross 1 embeds to two different numbers, right? So let's say embeds to B cross cross 1 and C cross cross 1, we use the notion of equality to prove that these numbers are actually equal to each other. Now, one fundamental operation is reciprocals, right? So reciprocals, we define if x equals A cross cross B, then the multiplicative inverse, which is the reciprocal, is defined as B cross cross A. So we're swapping. So in subtraction, we swapped the order of the terms, and in reciprocals, we're also swapping the order of the terms. Namely, both of these has to be non-zero. All right. Now, this is enough to show that the set of all integers q, how do you draw blackboard q? I have no idea. Forms a field. Right? So this is basically, it forms a commutative ring. We also have the notion of multiplicative inverse, right? Subtraction, we can't have the multiplicative inverse of 3, because that would be 1/3. But with rationals, we can do that. All right. One last thing for rationals, we can order it just like the integers. That is, I can say stuff like, oh, x equals A on B is positive. Oh, yeah. I forgot. We can now switch this term to cross. That is, x divided by y is equal to x, y inverse. So we can cross out that notion, right? Because we can show that this notion of this is actually equal to this notion. So for ordering, we can say, like, oh, x equals A on B is positive, for positive integers A and B, and negative if and only if, like, x is equal to negative y for a positive rational y. So basically, it's positive if x equals A on B for some, let's say A prime on B prime, for some positive AB. And negative if it's the negation of that, right? So like negative 6 over negative 8. both of these aren't positive, right? But we can write that as a ratio of positive integers. So if it's positive, it can be written as a ratio of positive integers, and if it's negative, it can be written as the negation of a ratio of positive integers. Now we have trichotomy of the rationals and ordering of the rationals, but there's nothing new here. Just the same properties that we have from there's the same properties we have from the integers. We also have negation reverses order, so remember that. Okay, section 3 is about absolute value and exponentiation. So absolute value is defined as the absolute value of x is defined as x if x is positive, and negative x if x is negative, or if x is less than or equal to 0. I guess the pure way to do it is if x is less than 0. This is the symmetric way to do it. We can also define the notion of distance as the distance between numbers is the absolute value of their difference. Right. So properties of absolute value and distance. So this is actually, absolute value is a general thing, right? It's not just true for, we can have a norm of a vector space. We can have the norm of a p-adic number system. So this is actually just a property of norms or absolute value in general. Satisfy. Namely, we say like the notion of absolute value has to include these. So the absolute value of x is always greater than or equal to 0, and the absolute value is equal to 0 if and only if x equals 0. Also, a triangle inequality, very important. Very important. Make sure to remember this. Triangle inequality is going to come up a lot. The absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. I'll prove this one. Yeah, I'll definitely prove this one after we go through some other properties. Negative y less than or equal to x less than or equal to y is the same thing as y is greater than or equal to absolute value of x. Next, we have the absolute value of x times the absolute value of y is equal to the absolute value of x times the absolute value of y. Next are about distance, right? So next is distance forms a norm. So I'll actually write this. So two things form a norm, right? This is what norms satisfy. Sorry. This is unique to absolute values. Wait, no, it's actually not unique to. Let's just say norms satisfy this, right? Distance, the distance xy, actually, don't mind C. Norms don't have to satisfy C. But ABD, yeah, they should satisfy ABD. Distance satisfies A and B. And they also are symmetric. So those are the three things norms satisfy: AB and symmetric. Distance, yeah. Okay, so I'll prove triangle inequality, right? So, for triangle inequality, we have the absolute value of x plus y is less than or equal to absolute value of x plus absolute value of y. Okay, so we'll split this up into 4 cases, right? So we'll say case 1 is that x and y are positive. Then this is trivial. Case 2 is that x and y are negative. Well, then we have, let's say, x is equal to negative a for positive a, and y is equal to negative b for positive b. So the absolute value of negative a plus negative b is equal to the absolute value of negative a plus b. It's not hard to prove that negative a is equal to negative 1 times a, actually. So we can use this factorization. And now we have the absolute value of negative of something. That's always equal to a plus b. And this is also a property that, this is from D, right? So from this, we can go ahead and say that this reduces to the positive case. That is case 1. Now we have to show that, let's see if x is positive and 1y is negative, right? Or like the converse, or like the symmetry of this. X is negative and y is positive. Well, in this case, we do the same thing. Let's say we have negative x plus y less than or equal to absolute value of negative a is just a. Absolute value of y is just y, right? So we have this, right? So clearly, the right-hand side is positive, right? And the left-hand side is also positive. Okay. But what we can do here is we can show that, let's say, absolute value of minus a plus y, right? This is the absolute value of y minus a. The absolute value of y minus a is equal to the absolute value of a minus y. So for two cases, let's say a greater than y and a less than y, we can show, so for the first case, if a is greater than or equal to y, this is just a minus y. And in this case, this is obvious. Second case, a less than y, we can show that this is actually y minus a and less than or equal to a plus y. This is also obvious. So case 3 is also done. And for case 4, will be x equals 0, y is equal to positive. Case 5 will be x equals 0, y is equal to negative. Case 6 will be x is equal to 0, y equals 0. And these are not hard to prove on their own. And okay, so how can we be sure we've exhausted everything? Well, note that we've gone over all the cases for y, right? By trichotomy of integers, y is either positive, negative, or 0. So that's 3 cases there. By trichotomy of integers, x is equal to 0, positive, or negative. So that's the 3 cases right there. So why do we only have 6? Because we're taking off the case where they're different from each other. So positive, negative, 0, 0. So positive, negative, and 0, negative, and 0, positive. Okay, that was a lot. Okay, so next is the notion of e-closeness. So we say that two numbers x and y are e-close. So we'll say that x and y are epsilon close or e-close if the distance between y and x is less than or equal to epsilon. So there's a tons of stuff we can prove about epsilon closeness. Namely, we can prove that, like, okay, if x equals y, then this is equivalent to saying that y is epsilon close to x for all epsilon greater than 0. And it's also symmetric, right? If x is e close to y, then y is e close to z. Transitive as well. There's also a few other things that we want to note. It's that if x is e close to y and y is delta close to z, then x is epsilon plus delta close to z. There's a few other statements like this. They'll come up later, but one other thing that I want to go over is that if x and y are e close, right? then for all epsilon prime, if epsilon prime is greater than epsilon, then we have that x is epsilon prime close to y. Okay, final statement, because this is like a bit of an involved one. If x and y are e-close, and z and w are delta closed, then xz and yw, get this. Now, the proofs of these statements are also not hard. We've already established the rules of, basically we have arithmetic, right? We can use absolute value arithmetic, all this good stuff. This is epsilon times the magnitude of z plus delta times the magnitude of x plus epsilon times delta. Why? Well, this means that y minus x is, let's just consider the boundary case, right, where they're exactly this apart. And then let's multiply these two. So we get, if we multiply these two, we get yw minus xz. But we get, actually we get yw plus xz. But what do we also get? Well, and we want xz minus yw. So I'm going to take the negative of this and multiply. So, in fact, this is z minus w is negative delta. Oh, and I guess this should be absolute value. Let's just assume w log y greater than x, w greater than z. And then we do the multiplication. Delta, and we have like the few other terms here, and so on, right? So essentially, it's not hard to show that, like, oh, if I just do all these things, and instead of this, you do this, and instead of using the W log, we use like absolute values and whatnot, we get this statement here. An alternative way that you can do it is that, like, you can set A equal to y minus x, and B is equal to w minus z. So you can explicitly say, like, oh, that's the difference, right? And you can, like, use, like, oh, this difference is less than or equal to this, and this is less than or equal to delta, right? And you can show this A's and B's are precisely that. All right, then. And you can also use the triangle inequality as well when you're doing this. All right, we're going to do some exponentiation very quickly. So exponentiation, we're not extending it to the rationals, we're extending it to the z, right? So we're saying that exponentiation of a natural number, we've already defined that. But now let's define exponentiation to a, for rational numbers to a natural number. So we'll define exponentiation of a rational number to a natural number to be such that, like, if I have x to the n times x to the m, these are properties, right? I have these properties, right? We also have a few other properties. Like, one other thing that we can have is if x greater than or equal to y greater than or equal to 0, this means x to the n greater than or equal to y to the n greater than or equal to 0. If we have x to the greater than y greater than or equal to 0, then this preserves this under the case where n greater than 0. All right. So yeah, it's greater than or equal to, and if it's greater than 0, n is a natural number, by the way. It's not negative, right? So we have these x and y are rationals, and n is a natural number. Okay. So now what we can do is what we can do is that we can, and we can prove this all using induction. So now what we can do is that we can do negative numbers. Induction with the base case x to the 0 equals 1, and x to the n plus 1 is equal to x times x to the n. This is kind of what we're using induction for. We can do that x to the negative n is noted as the reciprocal of x to the n. So the notation kind of plays nicely there. Then you can reprove the same properties of exponentiation using the natural numbers. All right. Now let's move on to gaps in the rationals. Gaps in the rationals. So we say that for every rational number, for every x in Q, there exists a unique integer a. There's a unique integer a, such that a less than or equal to x, lesser than n plus 1. Namely, a is equal to the floor of x. That's the definition of a floor of x, right? How do we prove this? Well, that's just the Euclidean division algorithm, right? Rationals are between, right? So for any two rationals, there exists some z such that x less than z less than y, if x less than y. Namely, x plus y on 2 works. It's not hard to prove that this works. Now, Tao goes on to prove that x squared equals 2 is unsolvable in the rationals. I'm sure you guys have all seen this proof before, but I'll quickly go over it. So if x squared equals 2, let's just assume x is positive. For the negative, it's a very similar case. Clearly 0 doesn't work, right? So we can actually do x greater than 0. So assume x equals p over q. Then we have p on q squared is equal to 2. So p squared is equal to 2q squared, right? So clearly p squared is even. Why? Well, because it has 2 in it, right? And there's something that we can prove is that if p squared is even, then p is even. How do we prove this? Well, contrapositive. If p is odd, then p squared is odd. So we get p is equal to 2 times some k. So we do 2k squared is equal to 2q squared. 4k squared is equal to 2q squared, or that 2k squared is equal to q squared. So we can do the same thing here. Clearly q is even, right? So that's q equals 2r. And yet 2k squared is equal to 4r squared, or that k squared is equal to 2r squared. So notice that if pq is a solution, then kr is a solution. But what is kr? Kr is p on 2, q on 2. And so on. So notice we have like this infinite descent, right? So the next theorem is that infinite descents are not possible in integers. I'm just going to use naturals, right? Oops. Oh, man. Wrong page. Let's get back to where it was. Infinite descent are not possible in naturals. And we can assume P and Q are naturals, right? Because we're assuming it's positive. So infinite descent is essentially saying that like there exists no sequence of rationals such that like you have this infinite descent where each one gets smaller than the last. So we can show this by induction, right? So we can show that if we induct on like k, right? So we can show that like an is greater than or equal to some k for all n, right? So because how do we prove this? So let's prove that. K equals 0. Well, clearly all naturals are greater than or equal to 0. If an is greater than k for all n, then an is greater than an plus 1, which is greater than k. So therefore, an is greater than k plus 1 for all n. Right? So basically what we're assuming, this is the step, right? If an plus 1 is greater than or equal to k, well, an is greater than an plus 1. So therefore, an is greater than or equal to k plus 1. So we can prove that an is greater than or equal to k for all n. And therefore, because there's no natural number. Therefore, we are done. Okay. Now, one thing that we can prove, basically what we showed is that like all the numbers have to be infinite, which is not possible. Now, finally, we'll prove that we can get arbitrarily close to square root of 2. We can't reach it using rationals, but we can get arbitrarily close. So let's say we have x squared less than 2 less than x plus epsilon squared, right? We're going to prove that for any, however close we want, so for any epsilon greater than 0, we can get arbitrarily close to x. So for any epsilon greater than 0, there exists rational number x, q. There exists rational number q such that that's true. So how do we prove this? So we're doing contradiction, right? So let's assume that for any rational number, for any epsilon, there exists no rational number. So this is true. Okay. So we have x squared is less than 2. But we also have x plus epsilon squared to be less than 2. Why? Because we're doing for the sake of contradiction, right? So we're saying that like, oh, for epsilon, the rational number has to be less than 2, and the x plus epsilon has to be less than 2, right? So it can't equal 2, right? So let's just start with x equals 0 and induct. For x equals 0, 0 less than 2, and epsilon less than 2, we get epsilon less than 2. Okay. But for x equals 1, what do we get? We get 1 less than 2, and we get 1 less than, we get 1 plus epsilon squared less than 2. Oh, wait, this should be epsilon squared. Sorry, my bad. So then we get epsilon squared plus 2 epsilon plus 1 less than 2. Right? Okay, but we know that epsilon squared is less than 2. So therefore, we can show is that wait, this should be 1 equals 2. What we can show is that because we know that epsilon squared is less than 2, then epsilon squared. Oh, okay. No, I was inducting wrong. Sorry. This should be, we're inducting on x plus epsilon n, right? Instead of just n. So the n will be x equals epsilon. It's multiples of epsilon. That's what we're inducting on. So here we have that if, so basically this is an implication, right? If 0 is less than 2, then epsilon squared is less than 2. This will tell us that if epsilon squared is less than 2, then epsilon plus epsilon, or 2 epsilon squared, is less than 2. So on. We can prove that using induction, that if 2 epsilon squared is less than 2, then 3 epsilon squared is less than 2. So you can prove that n epsilon squared is less than 2 for any like natural number n using induction. Okay, but hold on, what does this mean? This means that essentially that what we can do using this notion is we can say that n squared epsilon squared is less than 2. for any natural number n. Okay, so this would mean that n squared is less than 2 epsilon squared. Well, this is clearly irrational. So basically what you're saying here is that we've already proven, right, that a rational has to be between two natural numbers. So you're telling me there's no natural number on here? So this is any natural number, right? There is no natural number such, for any natural number, this is always bigger. So there's no natural number on the other side. That's absurd. So therefore, we can get arbitrarily close to 2. All right, that's going to be it for this section. Next is going to be chapter 5, which is chapter 5 is where we really start getting into analysis. So yeah, we're going to be doing a lot more proofs. We're going to be doing a lot more rigorousness, and the videos are going to keep getting better. Hopefully, I'm trying my best. All right, thanks, and yeah, see you in the next video.